Welcome to This Explainer. I'm absolutely thrilled you're here today because we're going to decode something pretty wild. We're tracing humanity's relentless, centuries-long quest to calculate faster and, well, build smaller. It's a story packed with brilliant minds and just massive, exponential leaps in innovation. So let's go ahead and unravel the astonishing history of computers.
Okay, let's dive right in with a mind-bending question. Think about this for a second. If transport technology had developed as rapidly as computer technology, how long do you think a trip across the Atlantic Ocean would take today? Well, the answer is absolutely stunning. It would take mere seconds, just a few seconds to cross the entire ocean. That single idea right there, that perfectly captures the sheer velocity of the evolution we're about to explore. To make sense of this whole journey, here's our chronological roadmap. First up, fingers, beads, and gears. Then, the dawn of real computers, followed by Generation 1 vacuum tubes. Next, we hit transistors and circuits, into the microchip revolution, and finally, we fast forward to tomorrow.
Section 1. Fingers, beads, and gears, the primitive era of calculation.
You know, it's a super simple but profound fact. The very first calculating device, it was literally just the 10 fingers on a person's hands. I mean, this basic anatomical reality is the exact reason we still count in tens today. It's wild. And then, following fingers, the abacus was invented, right? Just a frame with beads moving left to right. But what's truly amazing is that the abacus was heavily used well into the 16th century. Heck, it's still used in some parts of the world today, simply because it requires absolutely no ability to read. Now, let's watch how this builds as we step into the 17th and 18th centuries. This era saw a literal explosion of brilliant mathematical minds. First, you got a Scotsman named John Napier. He devised a mechanical way to multiply and divide, which laid the total groundwork for the modern slide rule. Then, Henry Briggs takes Napier's ideas and produces logarithm tables, which, by the way, mathematicians still rely on today. And right around that same time, calculus is independently invented by the Englishman Sir Isaac Newton and the German mathematician Gottfried Wilhelm Leibniz. We're essentially looking at the underlying mathematical software of the world being written right here.
But all that complex math needed a machine to run it. Enter the first real calculating machine in 1820. And its secret? The number 10. This device depended on a series of exactly 10 toothed gear wheels. It's just a beautiful piece of mechanical simplicity, specifically created to save time and really cut down on those pesky human mistakes.
Which brings us to a pretty crucial vocabulary word from our text: devise. To plan or invent a complex procedure or mechanism. See, in 1830, the Englishman Charles Babbage didn't just build a machine, he devised the analytical engine. Showcased at the Paris exhibition in 1855, Babbage's engine was this incredibly bold attempt to cut the human being completely out of the calculation process. He just wanted humans to provide the initial facts and let the machine do the rest. Now, even though he never fully finished his work, Babbage devised the very concepts that became the bedrock for the computers we use today.
Section 2. Dawn of real computers. The World War II era leaps. Now, what's truly mind-blowing here is how rapidly innovation took off over a span of just 17 short years. In 1930, an American named Vannevar Bush builds the first analog computer, a device literally used in World War II to help aim guns. Fast forward to 1944, and Professor Howard Eiking, teaming up with IBM, completes the Mark I. That was the first digital computer that could crunch long lists of math at super fast rates. Just 2 years later, in 1946, engineers at the University of Pennsylvania build the ENIAC. And then boom, just 1 year after that, in 1947, John von Neumann develops this revolutionary idea of keeping instructions inside the computer's memory. Talk about a massive conceptual leap. Section 3, Generation 1, vacuum tubes, the 1950s giants.
So, we arrive at the first generation, officially kicking off around 1950 with machines like the UNIVAC 1. These beasts relied on parts called vacuum tubes. And hey, for their time, they were fast, performing thousands of calculations every single second. But there were some pretty major drawbacks. These machines were absolutely massive, taking up huge amounts of physical space. Plus, they were way less dependable. If even one vacuum tube blew out, the whole calculation could just grind to a screeching halt.
Section 4. Transistors and circuits. Shrinking size, multiplying speed. Just 10 years later, around 1960, a single hardware swap completely changed the game. Second-generation computers ditched those fragile vacuum tubes and swapped them out for transistors. The impact here? Totally staggering. These second-generation computers could do the work 10 times faster than their predecessors. Because of that little transistor, they were significantly smaller, way faster, and far more dependable. But here is the absolute crucial point. Just 5 years later, in 1965, the third generation hits. These machines tossed out individual transistors in favor of tiny integrated circuits. And the result? They could perform 1 million calculations a second. Yes, 1 million. That is 1,000 times as many as those first-generation computers could do just 15 years prior. Honestly, the scale of that spin increase is almost hard to wrap your head around. Section 5. The microchip revolution. The fourth generation arrives. To really grasp the fourth generation, we have to talk about one massive technological leap, and that is micro-miniaturization. Basically, this is the process of reducing circuitry so drastically in size that an entire integrated circuit can fit onto a single chip. It is the absolute defining secret behind the explosive growth of modern computing power that we all rely on today. So how does this micro-miniaturization actually work in the real world? Well, the text lays it out perfectly. Step 1, you take a square or rectangular piece of silicon, and we're talking incredibly tiny here, usually just 1/10 to 1/4 of an inch. Step 2, you literally etch or imprint several layers of an integrated circuit directly onto that tiny piece of silicon. And finally, step 3, you encapsulate the whole thing inside a protective armor of plastic or ceramic. And there you have it. That tiny little square holds the kind of power that literally used to take up an entire room.
Section 6. Fast forward to tomorrow. What's next?
All right, let's pull everything together with a quick recap. We've journeyed from the primitive times of the simple abacus right through the heavy mathematical theories of the 17th and 18th centuries. Then, the hardware finally caught up, with transistors in 1960 kicking off the second generation. And that led us rapidly to the now, the fourth generation of microchips. It's just this incredibly clear, unbroken line of human ingenuity. But that brings us to a pretty stark reality of all this rapid progress: the word obsolete. Meaning, of course, something no longer in use, completely out of date. The text makes a fascinating point here. It predicted decades ago that at the rate computer technology was growing, the absolute cutting-edge computers of that day would be completely obsolete by 1985, and definitely by 1990. The technology was evolving so insanely fast, it was essentially devouring itself. And that leaves us with a truly provocative final thought for today. Think back to that first comparison we made, crossing the Atlantic Ocean in mere seconds. With the unstoppable exponential rate that computer technology is still growing at today, how fast is the very device you're using to watch this explainer becoming obsolete? It's a thrilling, maybe slightly dizzying reality to think about. Thanks so much for joining me to decode this incredible history. And hey, keep your eyes on the future.